Hi everyone, welcome to today's coding session. Today I'll be solving the climbing stairs problem using Python. I will explain the problem, its constraint, and two approaches. A top-down dynamic programming approach, also known as memoization. This approach is considered a divide and conquer strategy, where the problem is broken down into smaller subproblems recursively. And we are covering an optimized bottom-up dynamic programming approach, also known as tabulation, because it uses table array to store results. As I code, I'll explain each step in detail. Near the end, I will compare time and space complexity. Let's get started. So the problem is simple. You are climbing a staircase, and it takes n steps to reach the top. Each time, you can either climb 1 or 2 steps. We need to find the number of distinct ways you can reach the top. For example, if n equals 2, the way are 1 plus 1 or 2. So 2 ways to reach the top. And here, if n equals 3, the ways are 1, 1, 1, or 1, 2, or 2, 1. So there are 3 ways to reach the top. Now that we understand the problem, let's think about the constraints. And here, we know that the number of steps is either going to be 1 or it's going to be a maximum of 45. This means n is always a positive integer and won't exceed 45. The results will fit within the range of a 32-bit signed integer because the Fibonacci sequence grows within safe limits for n less than or equal to 45. Since the maximum value for n is 45, we don't need to worry about excessive recursion depth or memory usage, but an optimized solution is still preferred for efficiency. All right, let's start with the top-down dynamic programming approach. This approach uses recursion, but with memoization to store intermediate results, avoiding redundant calculation. The idea is simple. To reach step n, you can come from step n-1 or n-2. Therefore, the number of ways to reach n is the sum of the ways to reach n-1 and n-2. This gives us the recurrence relation, which I want you to solve. So here, read this, and then when you get a chance, see which one is the correct answer. And if you know the answer, comment below, and I'll let you know if you're correct or not. We will use a cache in our problem to store intermediate result. If the result for a subproblem is already calculated, we'll return it from the cache instead of recalculating it. So let's implement the top-down approach first. So here, what we're looking for is if n is less than or equal to 1, we're going to return 1. And the reason for that is that when you do 0 factorial, for example, or 1 factorial, there is only one way to achieve that. And if n is in memo, then we're going to return memo n. And this pretty much means that we're going to return, that means if this is the case, it means that we already calculated this value, and we're going to return the unique ways to get to that step that we already calculated. And if we have not done so, what we're going to do is we're going to calculate the value, which would be, we're going to use the storage, we're going to call the function n-1 first for the step, and then we're going to pass the dictionary itself. And let me not forget that I need to create the dictionary. So we're going to pass the dictionary as well with any updates we already have, and we're going to add the steps again here. So n-2, since that's the other way of getting to the step. And then finally, we're going to return the value. And this is going to be how many distinct ways it is to climb to the top. So let's see if I made any errors. Climb stairs, n-1, n-2 in memo. And I got memo up here. So let's see. Okay, so what I forgot is that we are dealing with a class, so therefore I need to call self every time I call the function. Okay, so it passed both test cases. And let's see how it compares to others. Okay, so as you can see, it runs at 0 milliseconds, so it's very fast and it beats 100%. And is pretty good when it comes to memory efficiency in this case, since it's 12 megabytes. And it beats 82%. So this approach is actually very efficient. Now, let's take a quick look at some examples. So here is how recursion works in case you haven't done it before. In our case, it's gonna -1 so if you are start at step 4, you're gonna subtract 1, and you're gonna do the same thing all the way till you reach the bottom. And then this one is gonna be completed, and once this is completed, you're gonna go to the top, and this one will be executed. And then we'll go back here, and we're gonna realize that we already done this calculation, so we're gonna end up having the solution. Now, this is specifically how we do the problem. So we got, let's say we want to get a step 4. We're going to see, okay, well, is n less than, meaning is step 4 less than or equal to 1? False. So we're going to skip here. Is n in memo? False. So we're going to go here. So now we're going to do the calculation, which in our case here is going to be 3. It's going to do the same thing, and then we're going to go to 2. It's going to do the same thing, and then we're going to go to 1 here, which is the first thing we're going to calculate. And now when it says is 1 less than or equal to 1, we're going to return 1, since that's the case. And that's what we return here. And now we're going to go back to 0 so that we finish out this climb stair 2. Is 0 less than or equal to 1? Yes, so we're going to return 1. So now we just return 1, 1. And this completes these steps, which now is going to be 1 plus 1, which is down here, which will equals 2. And we're going to store it. To get to step 2, it's going to take 2 unique ways, and that's how we store it here. And now we're going to return back up here, because recursion works by going down, specifically since we're adding it, and then we're going to go back up. So now we're at climb stair 3, in which case we're going to go to, okay, is 1 less than or equal to 1? Yes. So we're going to return 1. And now we already calculated 2 from here. So it's going to be 2 plus 1, which will give us 3. Then we're going to store. To get a step 3, there are 3 unique ways. Now we're finally done with these 2, and we're going to go back up to step 4. And all we have remaining is 2. So now it's going to say is 2 less than or equal to 1? False. But we know we already calculated it, so we're going to return how many unique ways there is to get to step 2. And now that we're done here, now we know that is 2 from 2, which is here. And from 3, we also calculated that, which is 3. So now we get 3 plus 2 equals 5. So there are 5 unique ways to get to step 4. And these are the 5 unique ways. 1 plus 1 plus 1 plus 1. 1 plus 1 plus 2, which is just wrapping up these 2, and then just moving the 2 to the left and to the left as the other way of finding out the other step. And finally, adding these last 2. And now we know all 5 ways of achieving or reaching the 4th step. So next, let's look at the bottom-up approach. So we're going to keep the base case, and we're going to remove the memoization, as we won't need it. We're going to build a solution from the bottom up at this point. So we're keeping that. Now we're going to have first is equal to 1, and second. So let's make sure it's lined up. First is equal to 1, and second is equal to 1. And then we're going to iterate. In the previous recursive problem, we never actually initialized values, but here we are. So now we have index 0 and index 1. And now we're going to go through, starting at step 2, we're going to go through all the steps. And now we're going to do the calculation, which is first plus second. Let me spell it correctly. First plus second. And now first, we're going to give it the value of second so that we keep updating as we go. First, we'll have the value of second. And then second is going to have the value of current. And once we're done, we're going to return second, which is the current calculation. And let's see how this one runs. Okay, so it passed both test cases. And let's see how it compares to others. And as we can see, 12 megabytes is what we had before. So this one is also 0 millisecond, and it beats 100% just like the previous one. So it goes to show the time complexity is the same. And here we can see that before, I believe it was a little bit more memory that was required. Here is using less memory, 12 megabytes. So now let's do a quick example. And here's our example. So as we initialized originally, first for 1 and second to 1, which is we got here 1 and 1. So now we got 2, which is calculating for current, first plus second, which is giving us 2. And that's what we ended up having here. And now what we're saying is second, we're going to assign to first, which is the same thing as saying that here we have first, let's say, and we're assigning second to it. And the same thing now, current, second is going to be assigned current. And when we do this calculation, then we're going to go again through it, and we're going to go to 3 all the way till we get to the end step. And in this case, since we're doing n equals 4, we already did 1, 1. And all we're doing is a Fibonacci, as you can see, because it's going to be 1 plus 1, which will give us 2. And then again, it's going to be 1 plus 2, which will give us 3. And then 2 plus 3, which will give us 5. And that's how we calculate this problem. So let's compare the two approaches. The top-down approach is easier to understand if you're comfortable with recursion. It uses memoization to store intermediate results, avoiding redundant calculations. The bottom-up approach is more space efficient because it avoids recursion and only uses a few variables for storage. Both approaches have the same time complexity, as you can see here, but the bottom-up approach is generally faster due to the lack of recursion overhead. In conclusion, the bottom-up dynamic programming approach is the most optimized solution for this problem. It has a time complexity of O of n, as you can see here, and it has a space complexity of O of 1, as you can see here in the green dotted. So that's it for today's coding session. If you found this helpful, don't forget to like, subscribe, and hit the notification bell to stay tuned for more coding insights. Drop a comment if you have any questions or suggestions. See you next time.